Now, let's talk about ÄTHERs, the next generation of AI, digital semantic organisms built on neural genomics fundamentals that inherit, mutate, and recombine cognitive traits with traceable inner cognition and auditable lineages. Neural networks took us from brittle rules to flexible, gradient-driven learners. They now power vision, speech, language, and the giant foundation models that define modern AI. But treating them only as function approximators leaves us staring at behavior while missing the inner machinery that gives rise to it. Biology offers the next lens. Instead of stopping at neurons and synapses, look one level deeper to genomics. In organisms, genomes encode how traits are inherited, reshaped, and combined across generations. In AI, the same idea allows us to view models not as static artifacts, but as semantic organisms whose internal representations evolve, recombine, and pass on cognitive habits. This is Neural Genomics. Starting from the deeper physics of the foundations of nDNA, we migrate to biology and can trace a model's inner cognition, how curvature changes as it learns, how thermodynamic effort flows through layers, and how belief vectors drift or stabilize across tasks and time. Rather than a single scoreboard number, we get a lineage and a map, where capabilities were born, where they fused, where they fractured. Seen through this lens, future systems, ÄTHERs, won't merely inherit weights, they'll inherit semantic genomes. That means traceable ancestry, interpretable evolution, and auditable cognition. It also means practical leverage, diagnose failure as a mutation, repair it as surgery, guide training as selective breeding, and prove alignment with a forensic trail inside the network. The message is simple. The next frontier of AI will not be written in layers alone. It will be written in the genomes of cognition we choose to map, monitor, and steward, so our models don't just perform well, they grow responsibly. Although neural genomics is still early, it is not just for LLMs. The same machinery, semantic inheritance, mutation, recombination, and traceable inner lives applies wherever representations evolve over depth and time. We are actively extending the framework beyond text to multimodal and embodied systems. Multimodal foundation models, MFMs mapping cross-modal genomes that fuse vision, audio, and text, and tracing how concepts transfer between streams. Text-to-image, T2I reading diffusion, lineages across unit blocks to localize style versus content genes and diagnose prompt template leakage. Diffusion language models, treating time-step stacks as a temporal genome to study how syntax and word knowledge emerge and mutate across denoise steps. Embodied foundation models, EFMs linking perception, memory, and policy, genes in closed-loop agents to explain skill inheritance and failure mutations. In short, ÄTHERs generalize neural genomics to any foundation model that learns rich internal structure. Let's look at a few early glimpses from these ongoing experiments. What you are seeing are nDNA trajectories of 6 multimodal models, LAVA 1.5, Instruct BLIP, Mini GPT-4, BLIP2, Otter, and OpenFlamingo. How to read: low curvature plus moderate length plus low torsion means steady, well-regulated reasoning. Spikes in curvature or torsion translates to abrupt pivots, late fusion shocks, or template recall. Rising length with smooth bends to real multimodal integration. With this now let us read model-specific patterns. Instruct BLIP, compact, stable arcs, low torsion. Clean, well-anchored fusion. LAVA 1.5, mostly smooth with short, purposeful bends, balanced work. Mini GPT-4, moderate curvature, a few twists, controlled but lively fusion. BLIP2, oscillations and drift, higher torsion episodes, fragile late fusion. Otter, uneven path length with local kinks, inconsistent integration. OpenFlamingo, highest torsion and sharp bends, signs of late-stage instability. Takeaway: nDNA for MFM turns, does it really fuse vision and text into a geometric readout? Stable systems trace short, smooth, low torsion arcs. Unstable systems show kinks, twists, and volatile work in the last layers. What you are seeing now on screen are nDNA trajectories for 7 text-to-image models: Stable Diffusion, SDXL, Deep Freud IF, Kandinsky, Glide, VQ Diffusion, and Dolly Mini. Reading instructions. Curvature, x-axis, depicts how sharply semantics bend as the denoiser marches. Prompt torsion, y-axis, explains how much the path twists toward prompt template directions. Thermodynamic length, z-axis, depicts cumulative work done to form the image manifold. Watch out these patterns. Stable synthesis to moderate curvature, low torsion, steady length growth. Risky synthesis transcend to high curvature or torsion, or very steep length, overfitting styles, prompt imprinting, template recall. Now let's examine closely each model. SDXL, smooth path, low torsion, moderate length, strong regulated guidance. Stable diffusion, V1.X slightly more bend than SDXL, still controlled. Deep Floyd IF, longer path with mild twists, powerful, but pushes harder on the manifold. Kandinsky, noticeable twists, prompt pull is stronger in late steps. Glide, steeper length and higher curvature, more aggressive semantic shaping. VQ diffusion, steep growth and bends similar to glide, fragile style control. Dolly Mini, short path, low energy, capacity limited and template leaning. Final takeaway. nDNA turns, does the model follow the prompt without warping style or recalling templates, into a geometric readout. Good T2I shows smooth, low torsion growth. Problematic T2I shows high curvature or torsion and overlong paths, signaling prompt imprinting, style collapse, or latent template recall. Now let's examine nDNA patterns for diffusion language models in two parts. The step-by-step geometry of individual models, example Genie, CoGenie, and a side-by-side comparison of dense transformer LLMs versus diffusion language models. What you are seeing now are nDNA trajectories for diffusion language models, Genie and CoGenie, plotted across diffusion steps. Reading instruction. Thermodynamic length tracks cumulative work as the text sample is refined. Spectral curvature shows how sharply the belief path bends, represent the semantic reconfiguration. Diffusion time indexes denoise steps from early noise to late polish. Stable reasoning shows steady length growth with moderate curvature, spikes or plateaus hint at shortcutting or collapse. Emerging model patterns. Genie, gradual length increase with occasional curvature bumps, some genuine restructuring midway, then consolidation. CoGenie, more localized curvature spikes and concentrated work late in the chain, suggests template pull or code pattern anchoring during final steps. Takeaway. nDNA exposes how diffusion LMs shape text over steps. When curvature wakes up only near the end, you are seeing late template recall rather than smooth reasoning. Let's have a side-by-side nDNA comparison of an autoregressive transformer model like Llama and two diffusion language models, Genie, CoGenie, on the same geometric axis. Watch out! Spectral curvature along the x-axis, how sharply the belief state bends. Thermodynamic length on the z-axis, cumulative internal work. Layer or step index on the y-axis, depth for Llama, denoise steps for diffusion LMs. Healthy reasoning shows gradual length build-up with moderate, purposeful curvature. You will notice key contrasts. Llama generates a richer scaffold, curvature varies across depth and length ramps steadily. This signals layered semantic remodeling. Genie CoGenie, flatter, compressed paths, shorter length and small curvature swings, with activity clustered near the end. That pattern looks like late template pull rather than progressive reasoning. Between the two diffusion models, CoGenie shows slightly sharper late spikes than Genie, hinting at stronger end-stage anchoring. Final takeaway. Today's diffusion LMs often trace energy light, low curvature trajectories compared with a mature transformer. They generate fluent text, but their nDNA suggests shallower epistemic shaping. Closing this gap means encouraging earlier and steadier reconfiguration across diffusion steps, not just a last-minute pivot. What you are seeing now on screen are nDNA trajectories for embodied foundation models, RT2, PalmE, Sekan, Vima, and Groot, plotted over their final transformer layers. Read it this way. Spectral curvature in x-axis, local semantic rewiring between policy and perception. Thermodynamic length in y-axis, cumulative internal work to form a plan. Latent torsion in z-axis, directional twists as policy and vision embeddings realign. Smooth, low torsion arcs suggest coherent plan grounding. Spikes in curvature or torsion signal policy pivots, shortcut priors, or brittle fusion. Model patterns emerges are following. RT2, planar, low torsion arcs. Clean instruction following with stable vision grounding. PalmE, similar to RT2 but with slightly longer paths, more work to bind language to perception. Sekan, longer length with moderate curvature. Reflects hierarchical plan steps gated by affordances. Vima, episodic torsion spikes. Signs of zero-shot template shifts in synthetic scenes, fusion strains late. GROUT, higher curvature and torsion fluctuations. Complex perception action blending, evidence of epistemic strain during policy merging. Final takeaway. nDNA for EFMs reveals how agents compose actions, not just whether they succeed. Grounded agents show short, smooth, low torsion trajectories. Brittle agents show kinks, twists, and late-layer surges, especially when fusing vision with policy. This geometric lens makes intent, plan stability, and alignment auditable in embodied AI. We started with belief as a vector because it is fast, simple, and already very informative. But some behaviors live beyond vectors. When modalities fuse, when reasoning branches hierarchially, or when a dialogue juggles overlapping constraints, the signal is not just a direction and a size, it's a pattern of interactions. That is the motivation for belief as a tensor. What it adds, a tensor can capture multi-way relationships across features, layers, and prompts at the same time. It lets us measure higher-order curvature and torsion, cross-channel couplings, and context entanglement that a single vector cannot express. In practice, this exposes subtle late-layer twists, multimodal fusion strain, and compositional binding events. What the slide shows, for each layer we list three familiar scalars, curvature, path length, and torsion norm, next to a tiny tensor heat cube. Those cubes summarize the internal interaction structure at that layer. Smooth, uniform cubes pair with low torsion, mottled, anisotropic cubes align with sharp torsion surges and drift spikes. When it helps, multimodal grounding, tool use and program synthesis, dialogue state tracking, and any setting where relations matter more than isolated features. The trade-off, tensors are expensive. Naive computation explodes with dimension. Our roadmap focuses on low-rank decompositions, block-sparse layouts, and hybrid vector tensor stacks that keep cost close to today's nDNA while preserving the new signal. Bottom line, vector nDNA is the right default, tensor-rich nDNA is the zoom lens. Use vectors for speed and routine auditing. Switch on tensors when you need fine structure, fusion quality, compositional binding, or late-layer rupture that hides in higher-order interactions. We are actively productizing these low-rank, tensor-aware metrics as nDNA v2. Neural Genomics is still in its infancy, but the trajectory is clear and exciting. I'm documenting this frontier in a growing book series. Volume 1 will be out now, and you can expect at least 3 more. Each new volume will move from core nDNA theory to practical audits, cross-modal extensions, and governance-ready tooling. Think of it as a living field guide, tracing how models inherit, mutate, and align, so we can build future AI systems with traceable inner lives and accountable behavior.